It's a pleasure also to introduce Sandeep, and I want to thank Sandeep. He was the first person who said yes to presenting at this workshop. Sandeep is Marvell's Executive Vice President of Central Engineering System on Chip Group. In this role, he oversees the development of SoCs for various end markets in advanced process nodes. He's a recognized expert in digital and mixed signal design, IP, and product development. Prior to joining Marvell in 2019, he was at Intel as Vice President of Engineering, where he led the FPGA product and technology development. Prior to that, he held various senior engineering leadership roles at both Xilinx and Advanced Micro Devices. He's a long-term industry veteran. He's a proven innovator and has brought multiple CPUs, GPUs, FPGAs, SoCs, and custom designs to market, which together have generated billions of dollars in cumulative revenue. Uh, he earned a BE in electronics engineering from Bangalore University and an MS in electrical engineering from NJIT. He's also a graduate of the Stanford Executive Program. With that, let me turn it over to Sandeep to present.
Yeah, good morning. Thanks, Ravi, for enrolling me into this one, and thanks to all my fellow speakers as well. It will be a great. It's a great honor and my pleasure to be here. So let's get right into it. And I think there will be a lot of commonality in the first few slides, although Jan and I never talked about coordinating our slides, but it'll be good. One of the things that my talk will focus on is what is the role of chiplets and how do we look at the opportunity that it presents for the industry to come together to solve what we call at Marvell data infrastructure market. As you all know, explosion in data generation, which also means you have to transmit it from off-chip, compute, and actually store, has made hardware and silicon hot again. Hot in maybe air quotes in more ways than one. And this has also coincided with another inflection point of slowdown in PPA, performance power area / cost, with advanced process geometries, right? As a result of these diverging phenomena, there's an urgent need to look at not only end markets, but also different architectures. And that's where chiplets come in. And how do we implement these to scale up to the market needs of designing hardware for the future end markets in either the switch or compute or graphics and so on, and most certainly in advanced applications in AI and such. We look at why monolithic only solutions may not suffice. And Jan eloquently stated this, is we are at a very important starting point. Our chiplets are here to stay, and we will look at the opportunities they do present. But certainly what I think is will require a collaborative approach to solve the challenges across the industry, especially in looking at standardized interfaces instead of proprietary, for example. Why not only monolithic is, from a simplistic viewpoint, it is different functions don't always or can't always be on the same process or the same chip. Due to either the technology fit, readiness, whether it is SIGI process, RF process, they may not all be ready with the schedule. Hence, you also need to take a look at the cost structure of a particular product and all the functions that that you need to put in a particular product. The reticle is starting to get too small. So what does that mean? And I think Jan touched upon this, but here is some specifics of what does yield indicate in terms of die size. And there have been many publications on this, right? When you introduce a product in an advanced geometry, in the first 6 to 12 months in your yields, you probably want to do a smaller die, like 100 to 150 square millimeter. Sure, you can have larger dies or wafer dies, but your margins will suffer. In order to have a sustainable path to cost effectiveness, a modularity of architectures allow to go to the right side of the spectrum, where in the picture you would see that for smaller die sizes, you can get better yield. And that is an obvious thing, but that is very easy to say, but hard to do when you have to look at how architectures need to scale to a certain die size. So modularity also leads to better validation. Validation is a big cost driver too for complex chips. Through standard interfaces. Of course, that also means we have to solve the challenge of power, because if you are duplicating interfaces, you need to solve the challenge of power. So the key takeaway then is, at what point in a process lifetime would you introduce a die, and what size it should be? And how do you really map your architecture to be modular? Now, we'll take an example of a Marvell switch, or a switch for any particular segment. If you look at the center, actually, you have a lot of the I/O high-speed serial I/O SerDes. But in the middle, you actually have 2 or maybe 3 slices, and I would call that chiplets, because the functions that you need, especially for terabit switching, the monolithic nature is too small, and that is actually important, and it drives the center slices. Not only that, what happens with that is you can have the cost curve, smaller chips, better yield, lower cost. And when you look at either a 7 nanometer, 5 nanometer, or 3 nanometer and going forward, the tape out costs are also increasing tremendously. And with a combination of chiplets, it's going to become a package design play, and you can introduce multiple SKUs of the products. And so a lower tape-out cost on top of a validated chiplet strategy will give you more product SKUs that you can introduce into the market. And this is really why modularity is key, and that enables the cost curve. So what does that mean? That modularity is not free. We do need interfaces. Standardized interfaces are better. For example, what happens is if you have a chip which is too big, then you want to slice it such that architecturally they are possible to be on 2 smaller die, and we will look at in coming how that fits in with the cost equation. But then you need to have a chip-to-chip interface that requires duplicating the interface. So we need to pay attention to the power consumption, but also what kind of chip-to-chip interface that you need, whether you need a high bandwidth, high number of wires, low bandwidth, high number of wires, or a mix of all these things. In addition, there is issues like cache coherency and so on and so forth. So as a result, the choice of the chip-to-chip interface for various end markets is going to be critical to choose. So let's take a look at, if you have chiplets, area versus cost consideration. If there's a large die, reticle size 750 square millimeters, and you need to put the same function and split it, then you can do that with 2 smaller dies, much lower cost per square millimeter. And this is an example of a product that we have. You can afford to add the interface. Now, the question always comes down to how do we manage power? and there is some cost that we need to pay for the power penalty for duplicating of the interfaces. But the relative cost and the yield will certainly be solved by this by chiplets. Now, not only are the die costs and die yields, the package costs considerations are also hugely important. And this is just a different, what is the OSAT cost versus the number of IOs and the build-up layers that you may have. And if you need to take a look at the escape of the bandwidth of the IOs that is necessary, right? And you will really need to increase the size of the package. And somebody asked this question is, how big are the packages? The packages are getting fairly substantial for terabit switching, and typically driven by how much of bandwidth needs to get in and out of the chip, as well as the cost itself, as you can see, for build-up layers of 8 to 8 or 7 to 7 is getting prohibitive. And now you have a new other vector that has been introduced in the last 1.5 years, is the supply chain situation, right? And I'm sure we will solve that in a few quarters or a couple of years, but then, do you go 8 to 8 to even more? How does that scale? And then there's the optics piece of it, right? So explosion in data to get in and out of the chip has also increased. And then we have to focus on channel loss. Materials becomes a big, deal in modeling all these escapes too. And then that has an impact on SI/PI techniques and tools associated with that and so on. So it's not only cost, it's also the technical challenges too. So then let's take an example of what is a next generation network switch looks like. And if you look at this, in order to get more bandwidth out of it, your SerDes is also tapping out. You have obviously 112 gig SerDes. You can get the average chip bandwidth higher. So if you want to go from 25 terabits to 51 terabits and more, you can go from 56 gig to 112 gig and 224 gig, but they have their own challenges there. It drives greater than 90 millimeters package size, but the demand for data explosion and the bandwidth is not stopping. So we have to figure out, and this is where we'll talk about where this is heading, right? So it's not only, chiplets are one piece, but it is really the end markets are also a huge inflection point, and that's why we are scratching the surface today. There is still a lot of innovation that needs to come, and we have work to do. So let me give a test case example of why we need to look at interfaces as well. So if you want to do 50 terabits on one chip, you have the practical problems of shoreline or the chip edge. And if you have a long reach SerDes, which needs to be at 30 dB insertion loss and beyond, and most people require just different configurations as well. For example, do you need to have a PLL per lane? Then that increases the size. And of course, there are innovations of how your north-south orientation needs to be, what your bump pitch needs to be, etc. But at some point, physical dimensions, you can't beat it, right? So if you are doing double row of SerDes, then yeah, sure, you can look at 35 terabits, as you can see in the curves here, the green and the blue curves. You can get to with double stacking. Then there is the escape that you need to work through. That increases your package. So obviously now you're going up in the build-up layers. And so how do you solve this? Okay, we may have to solve it with a different standard. So let's say we don't do long reach, we do XSR, which is extra short reach. That's also a standard. But then you need to take a look at, okay, if you want to do a 50 terabit, with XSR, you can also reduce the power, the picojoules per bit, less than 1, less than 0.5, so on and so forth. But that also taps out too, and you can have different configurations, whether it's by 8 or by 16. But at the end of the day, we do need to take a look at multiple other things. So where I'm leading with this is there is the cost situation, but there are other solutions that we need to keep in mind as well. Hence, let's take a look at why do we do this? So we've gone through, chiplets are needed. There is the cost curve. There's the package complexity. Then there is also, in order to do this, you have to overcome some of the readiness, right? Technology scaling, as we all know, is not going at the same rate and pace as it used to go 10 years ago. And that's obvious. And so analog scaling has not been at the same rate. And the silicon cost of advanced geometries, whether you go to 5, 3, 2, is becoming prohibitive. So one of the things that people do, and this has been well published as well, is, can you do your mixed signal hard to design IP, which is not scaling in an n-1 node. And that could be in 10, 7, whatever it is. And then you do the core, whether it is your CPU, graphics, FPGA, switch, in a core that is faster and to get to the market, and use a standard. Maybe it's an AIB, maybe it's an XSR, maybe it's whatever your proprietary interface is. And that allows you the total cost of product development lower because you have validated your hard interfaces, which is your analog interfaces, in a previous technology node. So then is that enough? Now, that may not be enough either. So then you look at what are the solutions for integrated optics, right? Then you have silicon photonics. The future of scalable systems is really getting high bandwidth die-to-die interconnect. You can do chiplet-based switching, but where it is coming to roost is really enabling your next generation optical interconnect. Silicon photonics is also another area that is going to be here to stay. You need obviously proven optical and DSP technology, but there are enough research that's going on out there, and in terms of products as well, in compact form factor co-packaged optics. There is onboard optics, which is not as integrated, but co-packaged optics allows you the ability to get as much data in and out, because ultimately, what is the problem? The problem is to get data movement from one place to another as fast as possible, as cheap as possible, and that's where solutions for integrated optics comes into play.
Sandeep, would you mind if I break in and ask a question? Because it's
sure,
important.
Absolutely.
What is your opinion of thermal management, and how do you think thermal management will play, and what is the power anticipated here?
Yeah, so the thermal management is absolutely important to solve. However, it also depends upon, a huge data centers, the eco footprint is more important for power and thermal management. So you can go from 100 watts to 200 watts, depending upon, which rack system you do. So it's certainly an important metric, power as well as thermal. And but there are specific, power envelopes and thermal budgets that we have to hit anyway. Otherwise, we have no product. So that's absolutely an important part as you look at architectures. What innovations need to happen, and now going from copper to optics, it allows some of these managements to be done differently, but has other problems to solve as well. Alignment of lasers, modulation schemes, and the process technologies that are necessary for embedding lasers. So all these comes into play. So in a nutshell, and I'll give more, Ravi, so we can have more questions. In a nutshell, what I'm saying is it's not only chiplets from an electrical standpoint. I'm saying there is another vector where higher data rates and distance drive the move from copper to optics that has its own set of innovations that we need to do. And this is just a slide that we have from Cisco's where data rates are driving the move to optics and the distances that needs to do it needs to cover. So in essence, right, the future carrier and data center switching, I mean, this is an important market. You will have to, and you asked about thermal, right? Then there is, is it air cooling? Is it liquid cooling? What's the cost of that? As you do integrated co-packaged optics. And this is where I think the industry as a whole needs to come together, because this is not it's a very expensive problem to resolve for all of us, and we can't go at it independently. And that's why I am a big proponent of standardized interfaces and standardized modules, but that is really a place where I think there are many forums where we can discuss this. So in summary, right, chiplets and modular designs are for multiple reasons. Now, again, having said that, not every product need to be having a chiplet. That's, there are people who ask me that question constantly, and it's not really necessary, because it's not every solution, doesn't have to be the same peanut butter across the board. However, given the cost of development in advanced geometries, this becomes imperative for majority of compute and networking segments. Innovations have to be done on package technology, but also these advanced packages and chiplets provide path to co-packaged optics, which is the next frontier to cross. And with that, I do thank you for the time and happy to take any questions.
Sandeep, thank you. This was an excellent talk. There are a few questions in the chat window. Let me walk through them. The first is, you showed a Marvell switch. Was that implemented on two different technology nodes?
Yeah, so, in that picture that I showed, there are, in the center, there are actually two or three of the slices. That's on the same technology, but you can see the periphery was on a different process technology. And that allows you to mix and match and use. And somebody asked a question about harvesting chiplets. I didn't know whether harvesting meant using the chiplet in other applications in another thing. That's the way I viewed the question, but you can harvest, the periphery for a different product.
Yeah, no, that's absolutely right. That's another way of harvesting.
Yeah.
Then there are two other questions. One is, how far, if it will ever come, do you think we will integrate optical waveguides in laminate substrates?
I think there is a lot of research ought to be done still on that one. It'll take some time.
Nice. And another question was, is there a specific team at Marvell who's working on chiplets, or how is the work distributed in Marvell?
Yeah, so it's not it's really product specific, and I think we have more of a distributed way to look at it, because you have the SerDes and chiplets, that is its own, and then the product teams work together to figure out the core of the product. And so it is not a single monolithic team. It is a distributed team, just like a chiplet is.
What is the major, this is a very Marvell specific question. What is the major standard you are interested in? Open HBI, AIB, POW?
Yeah, so we have, we have looked at a bunch of wires. We also, due to our Aquantia, they had an AQ link, and we looked at that. We also support a standard interface like XSR. I am familiar with AIB given that I had spent my previous years at Intel. So, every interface solves a different problem, right? If you, sometimes you need to take a look at it. But today, we are looking at standard interfaces.
Got it. One more question. Can you provide some examples of how chip-to-chip interfaces affect package technology considerations?
Um, Certainly. I mean, for example, if you look at a AIB or one of the high number of connectivity, right, where there was more silicon interposer, a lot of connections. So if that is the chip-to-chip interfaces, then you have to figure out a different package technology, build-up layers, etc. Now, if it is, say, XSR kind of link, then we need to really look at what's the bump pitch, how the escapes look like, and what's the build-up layer, and it goes higher from there, right? So I think what happens is your choice of the chip-to-chip interface needs to be mapped to the cost of an equivalent package technology, because at the end of the day, where I look at it is, are we delivering the right performance power for the right package cost? That becomes a bigger deal. And now we have the more important and present problem of, if I choose a package technology today, do I have the substrate supply in 2 years' time?
Yeah, absolutely.
Right.
Another question we have is, what kind of die-to-die testability features have you needed to implement on silicon to guarantee outgoing full package quality?
Yeah, so one of the things is I didn't touch upon the DFX and testability. That in itself is a big piece of what do we do for loop back testing? Whether we decide on functional testing and what is functional loop back testing versus ATPG, on the digital side. All I'm saying is there are specific test structures that we build and test features in both the digital as well as the mixed signal interface, because that, if you look at it, is one of the bigger reasons for chip respins these days. Not getting the interface right and not getting the actual yield testing. So without going into much of the details on what techniques we've used, I think there is a big focus on that piece.
Fair enough. Another question we have is, when do you see CPU coming in? Will it be for 3.2 terabit per second IO? And maybe you should specify whether it's unidirectional or bidirectional while you answer.
So it is today. If you look at it, I mean, with our acquisition of Inphi, we already are doing CPOs in that. And is it all? We have the lasers and TIAs and drivers, but they're not all on the same piece of silicon. Obviously, they are in package and different MCMs and module. It's at module level. We are going to go and make further modifications in our next generations of chips, which and CPO will be there, and it will be starting off unidirectional but lead to bidirectional.
Got it. I'll squeeze in one more question, Sandeep. There is many here. What is the latency impact of segregating the PHY, the SerDes DDR/IO chiplet, away from the min chiplet?
I mean, latency is always especially if you look at PCI Gen 5, Gen 6, or there is a latency. But there are techniques where you can hide the latency, not all the time. So we have to really, and this is where the modular architecture thing, where we look at is where the latency is acceptable and where it is not. In some of the CPU applications, and depending upon the interfaces, in memory, maybe the latency is not acceptable. But in serial interfaces, it's okay
Yeah.
for a networking application. But it really, I mean, there is no free lunch,
Yeah.
right? It is all about trade-offs.
Yeah. No, that's fair. There are other questions, but we are at time. Sandeep, thank you very much. This was a really, really educational talk, and maybe we can figure out a way to answer questions offline. There's 4 unanswered questions in the Q&A.
Sure. Thank you again, Ravi.
So once again, thank our sponsors, Advantest, Omcor, and Synopsys, who made this event possible. Advantest rated the best ATE company 2021 in the VLSI Customer Satisfaction Survey of 2021. Omcor, as we heard an excellent overview from Dave as to their work, but as the leading OSAT with differentiators in the area of technology, quality, and service. Synopsys, with their vision for supplying solutions from silicon to software. And with that, I will thank everybody for joining us today. And once again, thank you for your attention and your participation. And we look forward to seeing you again tomorrow at 8 a.m. Pacific. Thank you.